Look up at the night sky and find that reddish dot among the stars. Mars, the fourth planet from the Sun. A frozen desert world where the atmosphere is so thin you couldn't breathe, where temperatures plummet to -195 degrees Fahrenheit, where dust storms can engulf the entire planet for months. It's a dead world, a cosmic graveyard that serves as a stark reminder of planetary mortality. But what if I told you this wasn't always the case? What if Mars was once a blue world, with flowing rivers, vast oceans, and skies thick with clouds? What if billions of years ago, Mars was so similar to Earth that life might have flourished there first? The story we see today is one of desolation, a rusty, barren landscape dotted with ancient craters and carved by long, dry riverbeds. When we look at Mars through our telescopes or study the images sent back by rovers, we see only death and emptiness. But this red planet holds secrets that challenge everything we think we know about habitability, about the requirements for life, and about the fragile nature of the worlds we call home. Here's the question that should fundamentally alter how we view our place in the solar system. What if Mars didn't just support life billions of years ago, but was actually more hospitable than Earth during the early chapters of our solar system's history? What if the story of life in our cosmic neighborhood began not with the blue world we inhabit, but with a planet that is now nothing more than a frozen wasteland? The idea seems impossible until you examine the evidence. Mars shows unmistakable signs of a watery past, so extensive that it rivals anything Earth has experienced. Ancient coastlines that once bordered seas larger than our Mediterranean, river deltas that speak of flowing water for millions of years, mineral deposits that could only form in the presence of abundant liquid water, and a magnetic field that once protected a thick atmosphere capable of supporting complex weather systems and, potentially, life itself. This matters because it completely transforms our understanding of habitability, evolution, and the prerequisites for life. We've always assumed Earth was the Goldilocks planet, the one world in our solar system that happened to be just right for life to emerge and flourish. But what if we've been looking at this backwards? What if Mars was the first Goldilocks world, and Earth was the backup plan? 4.5 billion years ago, when our solar system was still young and violent, Mars was a completely different world. Where we see rusty dust and barren rock today, ancient Mars was likely covered in vast oceans that may have contained more water than currently exists in Earth's Arctic Ocean. The northern lowlands of Mars, now a desolate plain, were once the floor of an ocean that stretched across nearly a third of the planet's surface. This wasn't just a shallow sea. Evidence suggests that Mars's ancient ocean was deep, possibly reaching depths of over a mile in some regions. Coastlines traced by orbiters show the unmistakable signatures of wave action, tidal erosion, and sediment deposition that could only occur over geological timescales. These weren't temporary floods or brief periods of melting. This was a stable, long-lasting ocean that persisted for hundreds of millions of years. The Martian landscape still bears the scars of this watery past. Valles Marineris, a canyon system that dwarfs Earth's Grand Canyon, shows clear evidence of water erosion on a scale that makes terrestrial river systems look modest by comparison. Ancient riverbeds snake across the Martian surface, some wider than the Mississippi, carved by flowing water that transported sediments and shaped the landscape for millions of years. But water was just the beginning. Ancient Mars had something even more crucial for habitability: a substantial atmosphere. Where today's Martian atmosphere is less than 1% as thick as Earth's, the ancient planet likely had atmospheric pressure similar to what we experience today. This thick atmosphere was dominated by carbon dioxide, creating a powerful greenhouse effect that kept temperatures warm enough for liquid water to exist on the surface. The presence of clay minerals across vast regions of Mars tells us that this wasn't a brief phase in the planet's history. Clay formation requires not just water, but stable water that persists for extended periods while interacting with rock. The types of clays found on Mars indicate that the planet experienced what scientists call a Pholocian era, a time when water was so abundant and stable that it fundamentally altered the planet's surface chemistry. Perhaps most remarkably, ancient Mars had a magnetic field. Today, Mars has no global magnetic field, leaving it defenseless against the solar wind that strips away its atmosphere. But billions of years ago, the planet's core was active, generating a magnetic field that created a protective bubble around the planet. This magnetic shield protected both the atmosphere and any life that might have existed on the surface from the deadly radiation of space. The greenhouse effect created by this thick CO2 atmosphere was essential for keeping Mars warm. Despite receiving only about half the solar energy that Earth receives, The greenhouse effect was so powerful that average temperatures on Mars may have been higher than they were on early Earth. While our planet was still largely frozen during the period known as the faint young sun paradox, Mars may have enjoyed consistently warm temperatures that made it the more hospitable of the two worlds. 4 billion years ago, Mars likely had an atmosphere comparable to modern Earth in density, though with a completely different composition. This ancient Martian atmosphere was dominated by carbon dioxide, with significant amounts of water vapor, nitrogen, and other gases that created a complex dynamic weather system. Clouds formed and dissipated across Martian skies. Rain fell on the surface, filling rivers and maintaining the vast northern ocean. Understanding what happened to Mars's atmosphere is crucial to grasping the magnitude of the transformation this world underwent. The Mars we see today has an atmosphere so thin that water cannot exist as a liquid on the surface. Any water that appears immediately boils away into the near vacuum of space. But this wasn't always the case. This atmospheric density also provided another crucial benefit: protection from meteorite impacts. Earth's thick atmosphere burns up most small meteorites before they reach the surface, but modern Mars offers no such protection. However, ancient Mars with its substantial atmosphere would have provided similar shielding, creating a more stable environment for any developing ecosystems. The weather systems on ancient Mars must have been spectacular. With a global ocean in the north and extensive landmasses in the south, the planet would have experienced dramatic weather patterns. Massive storm systems would have formed over the ocean and moved inland, bringing precipitation to regions that are now among the driest places in the solar system. Seasonal changes would have driven migrations of water between different reservoirs, creating the kind of dynamic, ever-changing environment that life seems to require. But perhaps most intriguingly, Mars's thicker atmosphere may have supported a phenomenon that never occurred on early Earth: a stable, long-term climate that remained conducive to life for hundreds of millions of years. While Earth's early climate was chaotic and unstable, ancient Mars may have enjoyed what scientists call a Goldilocks climate for far longer than our own planet. The transformation of Mars from a potentially habitable world to the frozen desert we see today didn't happen overnight. It was a gradual process that took hundreds of millions of years, driven by the death of the planet's magnetic field and the subsequent loss of its protective atmosphere. Deep within Mars, the same process that creates Earth's magnetic field was once active. The planet's molten iron core, stirred by convection currents, generated electrical currents that created a global magnetic field. This invisible shield extended far into space, deflecting the charged particles of the solar wind and protecting the planet's atmosphere from being stripped away. But Mars is smaller than Earth, with only about half our planet's diameter and roughly 1/10 the mass. This size difference proved crucial. Smaller planets cool faster, and Mars's core began to solidify much earlier in its history than Earth's core. As the core cooled and solidified, the convection currents that generated the magnetic field gradually weakened and eventually stopped entirely. The timing of this magnetic collapse was catastrophic for Mars's habitability. Evidence suggests that the planet's magnetic field began failing around 4.2 billion years ago and had largely disappeared by 3.8 billion years ago. This timeline is crucial because it coincides with what scientists call the Late Heavy Bombardment, a period when the inner solar system was pelted with asteroids and comets. Without its magnetic shield, Mars became defenseless against the solar wind. These high-energy particles from the Sun began stripping away the planet's atmosphere, molecule by molecule. The process was gradual but relentless. Over hundreds of millions of years, the thick protective atmosphere that had maintained liquid water on the surface was torn away and lost to space. As the atmosphere thinned, the greenhouse effect weakened, temperatures began to drop, the vast northern ocean started to freeze, and what didn't freeze began to evaporate into the thinning atmosphere, where it too was lost to space. The water cycle that had sustained Mars for hundreds of millions of years gradually ground to a halt. This wasn't just atmospheric loss, it was planetary death. Rivers stopped flowing, lakes dried up. The diverse weather systems that had shaped the planet's surface for hundreds of millions of years ceased to exist. Mars entered what scientists call the Amazonian period, an era of cold, dry conditions that has persisted for the last 3 billion years. The speed of this transformation, while slow by human standards, was catastrophically rapid by geological standards. A planet that had maintained stable, potentially life-supporting conditions for hundreds of millions of years was transformed into a frozen wasteland in what amounts to a cosmic blink of an eye. The story of ancient Mars isn't based on speculation or wishful thinking. It's written in the rocks, minerals, and ice of the planet itself, decoded by an army of robotic explorers that have transformed our understanding of the red planet over the past several decades. Every Mars mission has added crucial pieces to this puzzle. The Viking landers of the 1970s first suggested that Mars had experienced extensive water erosion. The Mars Global Surveyor revealed the full extent of ancient river valleys and what appeared to be shorelines of a vanished ocean. The Mars Odyssey discovered vast amounts of water ice buried just beneath the surface in the polar regions. But it was the arrival of sophisticated rovers like Spirit, Opportunity, Curiosity, and Perseverance that provided the chemical and mineralogical evidence that confirmed Mars's watery past. These robotic geologists have analyzed thousands of rock samples, each one telling part of the story of planetary transformation. The mineral evidence is particularly compelling. Curiosity's analysis of rocks in Gale Crater revealed extensive deposits of clay minerals that could only have formed in the presence of neutral pH water that persisted for extended periods. These aren't just traces of ancient water, they're evidence of long-term, stable aqueous environments that would have been conducive to life. Even more intriguingly, the rovers have discovered what appear to be ancient stream beds, complete with rounded pebbles that could only have been shaped by flowing water. The size and arrangement of these pebbles tells us about the velocity and depth of ancient Martian streams. Some of these waterways were apparently knee-deep and flowing at walking pace, creating environments remarkably similar to streams on Earth. Perseverance's exploration of Jezero Crater has provided perhaps the most compelling evidence yet of ancient Mars's habitability. This crater was once filled with a lake fed by at least 2 rivers. The rover has identified sedimentary rocks that formed at the bottom of this ancient lake, along with what appears to be a river delta where flowing water deposited sediments over thousands of years. The chemical composition of these sedimentary rocks tells an even more detailed story. They contain organic molecules, the carbon-based compounds that are the building blocks of life as we know it. While the presence of organic molecules doesn't prove that life existed on Mars, it demonstrates that the chemical prerequisites for life were present. Perhaps most remarkably, some of these rocks show evidence of repeated cycles of wetting and drying, suggesting that Mars's ancient climate was dynamic and variable rather than static. These cycles are particularly interesting to astrobiologists because similar wet-dry cycles on early Earth may have been crucial for the emergence of complex organic molecules and ultimately life itself. One of the most sophisticated tools in our arsenal for understanding ancient Mars is the MAVEN spacecraft, which has been orbiting the red planet since 2014 with a specific mission to understand how Mars lost its atmosphere. The data MAVEN has collected provides a detailed picture of atmospheric escape that confirms our understanding of Mars's transformation. MAVEN has directly observed the solar wind, stripping away Mars's atmosphere in real time. The spacecraft measures the rate at which different gases are lost to space and has found that Mars is still losing atmosphere today, though at a much slower rate than in the past when the solar wind was more intense. The isotopic composition of Mars's remaining atmosphere tells the story of this loss. When lighter isotopes of elements like hydrogen are preferentially lost to space, the remaining atmosphere becomes enriched in heavier isotopes. The current composition of Mars's atmosphere shows exactly this pattern, indicating that the planet once had a much thicker atmosphere rich in water vapor and other light molecules. MAVEN's measurements suggest that ancient Mars may have had enough water to cover the entire planet in an ocean 450 feet deep. This is a staggering amount of water, roughly equivalent to half the volume of Earth's Atlantic Ocean. The fact that most of this water is now gone, lost to space or locked away as underground ice, demonstrates the magnitude of the planetary transformation. The spacecraft has also revealed that Mars continues to lose water today, though at a rate that's tiny compared to the ancient catastrophic loss. Every second, about 2 pounds of hydrogen escape from Mars's upper atmosphere, carrying with it the memory of the water molecules from which it came. Over billions of years, this steady loss has removed an ocean's worth of water from the red planet. These measurements allow scientists to work backwards and reconstruct what Mars's atmosphere might have looked like billions of years ago. The picture that emerges is of a world with atmospheric pressure similar to Earth's, dominated by carbon dioxide, but containing substantial amounts of water vapor, nitrogen, and other gases necessary for complex weather systems and potentially for life. While most of Mars's surface has been modified by billions of years of erosion and dust storms, certain locations on the planet preserve nearly pristine records of ancient conditions. These geological time capsules provide our best evidence for what Mars was like during its potentially habitable period. Impact craters serve as some of the most valuable windows into Mars's past. When meteorites slam into planetary surfaces, they excavate material from deep underground, bringing ancient rocks to the surface and preserving them under protective rims of debris. Many of Mars's oldest and most interesting mineral deposits are found in and around these ancient impact sites. Gale Crater, where the Curiosity rover has been exploring since 2012, is one such time capsule. This 96-mile-wide crater was formed by an impact that occurred after Mars's wet period had already begun. The central mountain in the crater, called Mount Sharp, is composed of layers of sedimentary rock that were deposited over millions of years when the crater was filled with a lake. Each layer in Mount Sharp represents a different period in Mars's climate history. Lower layers formed when the lake was deep and stable, while upper layers show evidence of a gradually drying climate. By driving up Mount Sharp and analysing these layers in sequence, Curiosity is essentially travelling through time, reading the story of Mars's transition from wet to dry conditions. Jezero Crater, where Perseverance is currently exploring, represents another crucial window into ancient Mars. This crater contains what appears to be one of the best preserved river deltas in the solar system. The fine layers of sediment in this delta were deposited by flowing water over thousands of years, creating a detailed record of ancient Martian hydrology. The rocks in Jezero Crater are particularly exciting because they formed during Mars's Noachian period, the earliest era of Martian geology when conditions were most likely to support life. These rocks have been sitting on Mars's surface for over 3.5 billion years, potentially preserving chemical and even biological signatures from the planet's most habitable period. Deep beneath Mars's surface, additional time capsules may be waiting. Subsurface ice deposits contain atmospheric gases trapped from ancient periods, while buried sedimentary layers may preserve even more detailed records of past climate conditions. Future Mars missions may be able to access these deeper archives and read even earlier chapters in the planet's history. The possibility that Mars once supported life isn't just speculation, it's a scientific hypothesis, supported by a growing body of evidence that Mars possessed all the ingredients necessary for life as we know it: liquid water, energy sources, and the chemical building blocks of biology. During its wet period, Mars would have offered numerous environments where life might have emerged and flourished. Ancient lakes and rivers would have provided stable aqueous environments protected from the harsh radiation of space. Hydrothermal systems, evidenced by certain mineral deposits, could have provided energy sources for primitive organisms. The planet's dynamic climate would have created diverse ecological niches. The organic molecules discovered by Mars rovers add another piece to this puzzle. While these carbon-based compounds could have formed through non-biological processes, their presence demonstrates that the chemical prerequisites for life were available on ancient Mars. On Earth, similar organic molecules in ancient rocks often represent the remains of primitive organisms. Some researchers have suggested that life might have originated on Mars before spreading to Earth. This hypothesis, known as panspermia, proposes that microorganisms could have traveled between planets on meteorites ejected by impacts. We know that Martian meteorites regularly reach Earth, and some of these rocks show evidence of having been blasted off Mars while the planet still had liquid water on its surface. If life did emerge on Mars first, it might have had a significant head start over terrestrial life. Mars cooled and developed stable surface conditions hundreds of millions of years before Earth. While our planet was still being bombarded by planet-sterilizing impacts during the late heavy bombardment, Mars may have already developed complex ecosystems. The search for evidence of ancient Martian life continues with each new mission. Perseverance is currently collecting rock samples that will eventually be returned to Earth for detailed analysis. These samples may contain fossilized remains of ancient Martian organisms or chemical signatures that could only have been produced by biological processes. Even if Mars never supported life, its history as a potentially habitable world has profound implications for astrobiology. It demonstrates that habitable conditions can emerge early in a planet's history, and that the requirements for life may be more common in the universe than we previously thought. The transformation of Mars from a potentially habitable world to a frozen desert offers sobering lessons about planetary habitability and the fragility of the conditions that support life. Mars serves as a natural experiment in planetary evolution, showing us what happens when a world loses the key ingredients for habitability. The role of planetary size in maintaining habitability cannot be overstated. Mars's smaller size led directly to its early cooling, the loss of its magnetic field, and ultimately the death of its atmosphere. This suggests that there may be a minimum planetary mass required for long-term habitability, with smaller worlds inevitably losing their atmospheres to space over geological time. The importance of magnetic fields for protecting planetary atmospheres is another crucial lesson from Mars. Without its magnetic shield, even a thick atmosphere can be stripped away by stellar winds over hundreds of millions of years. This has implications for the habitability of exoplanets, particularly those orbiting close to active stars. Mars also demonstrates that habitability is not necessarily permanent. A world that supports liquid water and potentially life for hundreds of millions of years can still undergo catastrophic climate change that renders it uninhabitable. This perspective is particularly relevant as we grapple with climate change on our own planet. The speed of Mars's transformation is equally instructive. While hundreds of millions of years seems like an eternity by human standards, it's relatively rapid by geological standards. This suggests that planetary climates can undergo dramatic shifts more quickly than we might expect, with implications for both past and future habitability. Perhaps most importantly, Mars shows us that Earth's current habitability is not guaranteed to persist indefinitely. Our planet's magnetic field, while currently strong, will not last forever. Our atmosphere, while currently stable, could be altered by various catastrophic events. The story of Mars reminds us that habitable worlds are precious and fragile. While Mars's surface is now too cold and dry to support most forms of life, the story of Martian biology may not be over. Deep beneath the surface, conditions might still be suitable for certain types of organisms, particularly those that don't require sunlight or surface water to survive. Earth hosts a vast subsurface biosphere, with microorganisms living in rock cracks and underground water systems miles below the surface. These deep-dwelling organisms derive energy from chemical reactions rather than sunlight, and can survive in conditions that would be lethal to surface life. Similar organisms might persist in Mars's subsurface even today. Evidence for subsurface water on Mars continues to accumulate. Ground-penetrating radar has revealed what appears to be a large underground lake beneath Mars's south polar ice cap. Seasonal dark streaks on Martian slopes may be caused by briny water seeping from underground sources. These discoveries suggest that liquid water, essential for life as we know it, still exists on Mars in hidden reservoirs. The discovery of methane in Mars's atmosphere has added another intriguing possibility. On Earth, much of the atmospheric methane is produced by biological processes, while geological processes can also produce methane. The seasonal variations and localized sources of Martian methane detected by various spacecraft suggest that biological processes cannot be ruled out. If life does survive in Mars's subsurface, it would represent an incredible feat of endurance. These organisms would be survivors of one of the most dramatic planetary catastrophes in the solar system, having adapted to increasingly harsh conditions over billions of years. They might preserve genetic and biochemical information from Mars's ancient biosphere, providing a living link to the planet's habitable past. Future Mars missions are specifically designed to search for signs of current life in the planet's subsurface. The European Space Agency's ExoMars rover, when it eventually lands, will be equipped with a drill capable of reaching 2 meters below the surface, where organisms might be protected from radiation and have access to underground water. Understanding exactly how Mars transitioned from a wet, potentially habitable world to the frozen desert we see today is crucial for understanding planetary evolution and the long-term prospects for life in the universe. This transformation, known as the Great Drying, represents one of the most dramatic climate changes in the solar system's history. The process began with the weakening of Mars's magnetic field around 4.2 billion years ago. As the planet's core cooled and solidified, the convection currents that generated the magnetic field gradually weakened. This left Mars's atmosphere increasingly vulnerable to the solar wind, which began stripping away gas molecules at an accelerating rate. The loss of atmospheric pressure had cascading effects on the planet's climate system. As atmospheric pressure dropped, the boiling point of water decreased, making it increasingly difficult for liquid water to remain stable on the surface. Bodies of water that had persisted for millions of years began to boil away, adding water vapor to the atmosphere where it could be more easily lost to space. The greenhouse effect that had kept Mars warm despite its distance from the Sun began to weaken as carbon dioxide was lost to space. This cooling created a positive feedback loop. As temperatures dropped, more water froze into ice, removing water vapor from the atmosphere and further weakening the greenhouse effect. The planet's weather systems, once dynamic and complex, gradually simplified and weakened. The vast northern ocean began to freeze and eventually sublimate away. Rivers stopped flowing as their sources dried up or froze. The diverse climate zones that had characterized ancient Mars collapsed into the single monotonously cold and dry climate that dominates the planet today. This wasn't a sudden catastrophe, but a gradual decline that took hundreds of millions of years. During this period, Mars likely experienced brief episodes of renewed activity when volcanic eruptions released water vapor and other gases into the atmosphere, temporarily thickening it and allowing liquid water to flow on the surface again. But these episodes became less frequent and less significant over time as the planet's internal heat engine wound down. The story of Mars's transformation from a potentially habitable world to a frozen wasteland has profound implications for understanding the long-term future of our own planet. While Earth is currently much more geologically active and massive than Mars, our planet faces similar challenges over cosmic timescales. Earth's magnetic field, currently strong and stable, is generated by the same process that once protected Mars. Our planet's larger size means that its core will remain molten and active for billions of years longer than Mars's core did, but it will eventually cool and solidify. When that happens, Earth will lose its magnetic protection and begin to experience atmospheric loss, similar to what befell Mars. The solar wind that stripped away Mars's atmosphere will also grow stronger over time, as our Sun ages and becomes more active. In about 5 billion years, the Sun will begin its transformation into a red giant star, dramatically increasing the intensity of stellar winds that could strip away planetary atmospheres throughout the solar system. But Earth faces more immediate challenges as well. The gradual increase in solar luminosity over the next billion years will eventually make our planet too hot to maintain liquid water on its surface, regardless of atmospheric composition. This natural warming will eventually trigger a runaway greenhouse effect that could transform Earth into a world more like Venus than the habitable planet we know today. The story of Mars also highlights the importance of planetary mass for long-term habitability. Earth's greater mass has allowed it to retain its atmosphere and maintain active geological processes for billions of years longer than Mars could. This suggests that when we search for potentially habitable exoplanets, we should focus on worlds that are at least as massive as Earth. Perhaps most importantly, Mars demonstrates that planetary habitability is not a permanent state, but a temporary phase in planetary evolution. Every habitable world will eventually become uninhabitable as its parent star evolves or as its own geological processes wind down. This perspective emphasizes both the preciousness of habitable worlds and the importance of eventually spreading life beyond single planets. As we look toward the future, the stories of Earth and Mars may become intertwined in ways that would have seemed impossible just a few decades ago. Human exploration and eventual colonization of Mars represents the next chapter in both planets' stories, potentially bringing life back to a world that may have once hosted its own indigenous organisms. Current plans for Mars exploration include returning samples to Earth for detailed analysis, searching for signs of current life in the planet's subsurface, and eventually sending human explorers to walk on its ancient lake beds and river valleys. These missions will undoubtedly reveal new details about Mars's transformation and may finally answer the question of whether life ever existed there. The possibility of terraforming Mars, while technically challenging, represents the ultimate test of our understanding of planetary climate systems. If we can successfully restore a thick atmosphere and liquid water to Mars's surface, it would demonstrate a mastery of planetary engineering that could have applications for maintaining Earth's habitability as well. But Mars also serves as a warning about the fragility of planetary environments. The same processes that could potentially restore Mars's atmosphere could also be used to destroy Earth's. Understanding planetary climate evolution is crucial not just for exploring other worlds, but for protecting our own. The red planet that shines in our night sky is both a graveyard and a time capsule. It preserves the story of its own transformation from a world that might have rivaled Earth in habitability to the frozen wasteland we see today. This story is written in its rocks, its minerals, its thin atmosphere, and the dry channels that once carried flowing rivers. The transformation of Mars from a potentially habitable world to a frozen desert represents one chapter in the larger story of planetary evolution throughout the universe. As we discover thousands of exoplanets orbiting other stars, many of which may have undergone similar transformations, Mars serves as a crucial reference point for understanding how common habitability might be and how long it might last. The early habitability of Mars suggests that the ingredients for life may be more common in the universe than we once thought. If a planet as small as Mars could maintain liquid water and a thick atmosphere for hundreds of millions of years, then many of the rocky exoplanets we're discovering might have had similar habitable periods, even if they're no longer habitable today. This has profound implications for the search for life in the universe. we may need to expand our search beyond currently habitable worlds to include planets that were once habitable but have since undergone dramatic climate changes. Some of these worlds might still harbour subsurface life, while others might preserve fossils or chemical signatures of past biological activity. The story of Mars also emphasizes the dynamic nature of planetary evolution. Worlds don't simply form and remain static. They evolve, change, and sometimes undergo dramatic transformations that completely alter their character. Understanding these evolutionary processes is crucial for predicting the long-term habitability of any world, including our own. Perhaps most importantly, Mars reminds us that habitability is temporary. Every habitable world will eventually become uninhabitable, either through internal processes like the loss of magnetic fields and atmospheric escape, or through external factors like stellar evolution. This perspective underscores the preciousness of life and the importance of understanding and protecting the conditions that make it possible. When we look at Mars today, we're seeing both the past and the future. We're seeing what Earth was like billions of years ago when both planets were young and potentially habitable, but we're also seeing what Earth might become billions of years in the future when our own planet's geological processes wind down and our protective magnetic field weakens. The red planet serves as both a warning and an inspiration. It warns us about the fragility of planetary environments and the temporary nature of habitability, but it also inspires us to continue exploring, to keep searching for signs of life beyond Earth, and to work toward ensuring that life itself, whether terrestrial or extraterrestrial, has a future beyond any single world. In the end, Mars is more than just our planetary neighbor. It's a mirror that reflects both our past and our future, a laboratory for understanding planetary evolution, and possibly a stepping stone toward becoming a multiplanetary species. The story of when Mars was like Earth is also the story of how worlds change, how life adapts, and how the universe itself continues to evolve. It's a story that's still being written, both in the rocks of the red planet and in the minds of those who dare to explore beyond the boundaries of our blue world.